Welcome. This is a new module about differential calculus. This is a long module. It's 8 hours, so it will cover a period of 4 weeks, and this will be like a crash course in differential calculus. For some of you, about half of this material will be basic, so please be patient. But for some of you, this could be challenging, especially if you have no prior calculus experience. So if you find the material challenging, please contact like the instructor. Let the instructor know immediately. Yeah. So here, this is the course description according to the university catalog, and you see big part of it, all these in red is about calculus. So in order not to make one big module, I divided all these calculus into like 3 modules. So Calc 1, Calc 2, Calc 3. Does it ring a bell? Okay. So Calc 1, we will be mainly dealing with differential calculus. Calc 2, we will be dealing with integral calculus. And then we will bring these two guys together and talk about differential equation. And differential equation, these are the building block of physics-based modeling. Not physical modeling as we did in numerical analysis, but physics-based modeling where you have some uh, equations. These equations are generally would be based on the conservation law, like conservation of mass, conservation of energy, conservation of momentum, and then you use these equations to describe your system. So these are the basics of modeling, and then linear algebra. These 3 module, Calc 1, Calc 2, and Calc 3, these are some of the references that I use to prepare these lessons. These are some of the references. So I have these books in my office if you want to check them out. Use these references if you want to learn more about the material covered. Again, like the material cover is not only from this book, like but especially the FE exam type of questions. So a lot of them are inspired by the material here. Not only here, but here and other similar FE exam books. So if you want to practice more, these are just some suggestions for practicing more, especially for FE exam, or any similar book FE exam books that you have. Okay. Uh, so you don't need to uh, get these book. If you have any similar one, that's the same because they are all the same ideas and they will all cover like similar topics or same topics. Yeah. So let's just so this module like have 5 lesson. Again, the learning objective is build essential calculus skill for FE exam and engineering application, and I will be accommodating for varying levels of prior knowledge. Yeah. So there will be fundamentals of derivatives. That's lesson 1 in 1 week. So which has like 3 parts: fundamental theorem of calculus, which is this video, derivative law rules, and derivative of special functions. And we will be moving to how to apply these things in something like an optimization problem. So we will be learning more concept like singular and critical point, and we'll be applying what we learned to optimization problem, and we'll see some engineering application for this. But then we will shift gear to multivariable derivative. So like usually, like here, we'll be dealing like f of x, but usually we have multivariable, like your function could be f of x, y, z, and maybe time, yeah? Something that's changing in space and time. So we will be dealing with this here, and particularly we will be looking at this concept of partial derivative, and that would be mainly an introduction to vector calculus. And vector calculus, we will learn like the building block of vector calculus, gradient, diversion, uh, gradients or gradients, but divergence and curl. And this is essential knowledge that you need for to understand differential equation and for new modeling, like physics-based modeling. That's the building block of these guys. And then we will finally, like the last lesson, will be like Taylor series, and in this Taylor series, this is important because part of the analytical solution. So you have differential equations, the analytical solution of this differential equation. Sometimes you will use series expansion like this called infinite series solution. But most importantly, this would be important for numerical solutions. So you have like a differential equation. Some of these differential equations, they don't have an analytical solution, like not a closed form or an infinite series solution, and you need to solve it numerically, and that's why this guy is important. Yeah, but let's just do it one by one. So this is like 1 week, this is 1 week, this is 1 week, and these two guys will be covered in 1 week, so that's like a total of 4 weeks. Okay. uh, so let's just start here with lesson one, which is like fundamental of derivatives, and this video will be part one, which is the fundamental theorem of calculus. So fundamental of derivatives, the part one, the fundamental theorem of calculus. So the objective of this part, like the fundamental theorem of calculus, is that we will understand the fundamental theorem of calculus. You will know by the end of this video, you will know what this is. But more importantly, you will know why this is important. Why this is something very important in life, and this is something central to a lot of what we do in engineering, the fundamental theorem of calculus. So let's start. Okay, so calculus. So if you don't like, if you don't know, calculus is the related mathematical concept of differentiation and integration. So what is this? Okay, what is like differentiation and what's integration? Okay, so let's here look at a function. So calculus basically like differentiations. That's like deal with changes, something that it changes. So like let's when we do like differentiation, so we have like a function. Yeah, we have a function. When we differentiate this function, yeah, we get like this is called like the derivative, and this derivative, so like I have a function. When I differentiate this function, I get like the derivative of this function, and this derivative is basically the rate of a change of this function. And so I have a function, and I want to know what is the rate of a change of this function. So you see the rate of a change in this function here is not much. Here, like it's very like the rate of a change here is very large, because you see this is steep, like it's going up, so the rate of a change is larger than here, for example. Okay, and this is important because any system that we are dealing with in engineering, if we know the rate of a change along this system, we can model and understand this system. Flow, for example. So flow, why does flow occur? Flow occurs because there is like a change in energy. So flow will occur from high energy to low energy. So you have like high energy in some point in your system, low energy in some point in your system, and this energy gradient will push the fluid, and then flow will occur. So we want to know this rate of a change. If we know like here the rate of change is low, here the rate of change is high, then we will be able to understand the system. Know like here is like laminar, this is turbulent, and then we will be able to find an equation that describes the system in terms of the rate of change of energy, for example. That would be like the one of the flow equation, and then you can use this equation to model and study or do your design. Yeah, so that's so again, like you have a function and derivatives. This is like this is called like the derivative of a function. This is the rate of a change. So here I want to find like the rate of a change. So how could I find like this rate of a change like at a point? So basically I could, so this is a point. I could draw like a tangent at this point. So I have a point. If I draw a tangent, like I have a point here. If I draw like this tangent along this point, then I find the slope of this tangent. That would be like the rate of a change along this point. Similarly, like what is the rate of a change along this point? So I can make it here. I can draw I can draw like a tangent, and then the slope of this tangent would be the rate of a change. So the slope of this tangent, for example, will be positive because I'm going up. If I draw like what is the rate of a change here at this point, if I draw like a tangent here, yeah, and then I found the slope of this tangent, and the slope of this tangent will be negative. So the rate of a change is negative. You see here, the slope here is mild versus the slope here is more steep. And that's exactly because the rate of a change here is higher. That's why I can go up very quickly. Here I'm going down slowly, but here I'm going up very quickly because it's steeper. Here it's negative because I'm like sloping, I'm going down. Here it is positive because I'm rising, I'm going up. So that would be how the slope. But this is just to understand. But how could I actually do it? Like how could I find this value here? Yeah, how could I exactly find like the tangent? So one way to do this is I could draw, for example, like this secant line. Yeah, so I can draw like a secant line here. Yeah, try to, so I can here uh, draw like this secant line. And basically, so this secant line, so here, this is my x. So this is like, let's say, any x, and then that here would be my x plus delta x. Delta x basically is the distance from here to here. That's like delta x, yeah? So I can, I mean, the secant line does not look so good. Let me try to, okay, whatever. So I can do this, and then basically, like, so what is the slope of this line? Now I know how to get the slope of this line because the slope of like this guy, that is delta y over delta x, yeah, or delta y. So that's like my, so delta y over delta x. So basically, like, what is the slope of this line? So that would be like this guy minus this guy divided by this guy minus this guy. So that would be equal to like my, so here this is like f of x delta x, and this is f of x, yeah. So that would be f of x delta x minus f of x, that's like how you find the slope, divided by this guy minus delta x. So this is basically delta x. So because when you understand, like, it will be like x plus delta x. So this guy here minus this guy here, and that will give you delta x. So that is divided by like delta x. So that's how I can find the slope. But I have a problem here. Is really, so is this secant line here? So this is secant, c, sorry, this secant. Is the slope of this secant line equal to the slope of this guy? I mean, it's an approximation. It's not a bad approximation, but it's not like a great approximation because, like, you see, the slope of this guy here is a little bit different than the slope of this guy. How could I solve this problem? Like, is there a way for solving this problem? Yes, there is a way for solving this problem. Like, this secant line is very long. How about if I made like a shorter one? So I can just make a little bit shorter one here. So now you see, now the slope of this guy, if I took like the slope, now let me delete this guy. If I now took this, like, so my delta x is getting smaller. So you see here, my delta x is getting smaller. And as delta x gets smaller, yeah, what happened? So as delta x gets smaller, then the slope of this guy is approaching to this guy. So here my delta x is getting smaller. Can I improve it? Yes, sure. How can I improve it? I can just like make like just a smaller secant line here and see like my delta x is getting smaller. See now the slope of this guy is almost the slope of this guy. What about if I make like this delta x, yeah? very, very small, like it approaches to zero, like extremely small. Yeah. So if I made like delta x like extremely small, it approaches to zero, then the slope of here at this point would be equal to the slope of like these tangents. So basically that is how we find the rate of a change at a point. So derivative is rate, so the derivative is that is the rate which can be, so derivative could be, I could like, so this is my f of x. Derivative is usually written like this, or sometimes it's also written that is equal to dy over dx. Yeah. So, or the, like your function f of x dx, or I mean all these are, yeah, all these are the same thing, f of x. Yeah. But so okay. So what is the derivative of this function? So this is a difference approximation. This guy here is a derivative. Let me bring this guy here. Okay. So this is slope is different approximations. The derivative would be, okay, would be like equal to this guy, like this difference approximation, f of x delta x minus f of x over delta x, but at the delta x approaches to zero. So like here you limit, so x approaches to zero, and that's the difference between like slope, like so this is like slope. That is the difference between like the difference approximation delta y over delta x versus, let me move this guy here. Let me write it again. So this is difference approximation delta y over delta x. This is the derivative dy over dx. What is the derivative? It is the limit as x goes to 0, and then you put your difference approximation. So it is a difference approximation, but your delta x is just like tiny little thing. Yeah, it's very small. How we are doing in time here. Not bad. Okay, so that is basically the definition of derivative. So I can, that's actually, that's a great conclusion that we reach it here, because what does this mean? This means if I can find the derivative, so I have like a function f of x, if I can find the derivative of this function, like this guy, which is equal to this guy, basically I could just find the rate of a change at any point, like here, 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 any point along my function. I could find this rate of a change, and I could see how this function is changing. Let me show you like an example here. Yeah. So you see, this is my function. So this is like the function that I have here. This is the derivative. I'm not showing you how like I'm calculating like what is the equation for this guy. Like don't worry now about like the equation for this guy. We will look at this equation, like how to go from here and find like an equation here and be able to calculate this. But now the most important thing what I want to see you here is that I'm showing you the rate of a change at a point. So you see the rate of a change here, for example, is 0. See, the rate of change here is negative. Here it is positive, and it should be very high. So look at this guy here. Yeah. So this is like different x value, and this is rate of change. So here is negative. Here is like 0. Yeah. Here is positive. See, here's the rate of change. If you look at this guy, it would be very small because this is not very steep. So the rate very small. Here it gets like another 0. And then here it start to become a steep, like very high rate of change. Here it is 0. And see now, like the rate of change is like negative, because I'm sloping down. Now here is 0. I'm sloping up, then it become positive. So you can see, and here again negative. Why is this important? So for example, like you see this guy here, you see this guy here, you see this guy here. The rate of change here is 0, like dy over dx here is 0. The rate of change here, dy over dx is 0. Does this look anything? This is like if you are solving an optimization problem and you want to find the maximum value. where would you find the maximum value? Look for maximum value when the rate of change is zero. That is where you get these peaks because you go to the top and then you drop. So when you stop, so you go all the way to the top, you rest here and then you start dropping, and then at this moment when you rest, that's when you get like one of these points. Yeah, but anyway, we will do this next week. We will be calculating this rate of change to solve this type of optimization problem. But for now, let's just move on. How can we move on from here? Okay, so let's go back to our to this guy. Okay, so again, calculus has to do with differentiation. Differentiation. What does differentiation mean? Differentiation mean like to go from my function to the rate of a change to this function. This is called differentiation. So opposite of differentiation. And here we are. What we are doing, we are trying. Like this guy is telling me the rate of a change. Integration is the opposite actually of differentiation. So while like a derivative is telling me about the rate of a change, integration, which is opposite of differentiation, is telling me accumulation, not the rate of a change. So I have like a function here, yeah, and what integration basically is telling me is accumulation. Like what is accumulating under this function? So for example, like I have this function, and if you want to know what's accumulating under this function, that would be just basically like the area under this curve. So I can basically, what I can do, I can find like the area under this curve from A to B. And that would be like accumulation. But accumulation could be like a volume of a sphere, could be a length of an arc, it could be like some contaminants that are being accumulated, or whatever, yeah, depending on like the context you put it. But that's the general idea. Like it could be interpreted as like area under the curve or like accumulation. So this is called integral. So like previously we find the rate of a change. Here we want to look at accumulation, and then this is called like the previous one. Like this guy was called like a derivative. This guy is called like an integral of the function, and the integral, it has like this sign. It looks like summation because that's exactly what I'm doing. Like I'm doing kind of like summation. So it looks like a little bit like summation. So this is integral, and this would be like I'm integrating my function over dx. So like dx here, like it's like every small, like, so basically like what I'm doing, I'm summing these function. So like I have like this guy here, yeah, and this is like my dx plus this guy here, and this is like my dx. So I'm integrating it. If I added this guy with this guy with this guy, I added like this guy with this guy with this, all of them all the way to the end, I will get like the area under this curve. So integration of a function with respect to its independent variable. So I have like a function f of x here. I'm integrating it with respect to my independent variable x, and I'm evaluating it like through this interval, like from A to B. So this is basically two concepts. One here is the rate of a change, and one here is like area under the curve of accumulation. Can we see these two together? Because if we put like these two together, like if we put this guy here, yeah, if we put like this guy here with this guy here, that basically will give us the fundamental theorem of calculus. So consider like spatial differentiable functions. We have a function here, yeah, that's like your function. Y of x is one dimensional system bounded by a and b. So I have a function, and what this is telling me, so this is my function, yeah, y of x from a to b, and so what this is telling me, the fundamental theorem of calculus is telling me, if I got the derivative of this function and I integrated it, I will get my function back. Does this make sense? So let me repeat again. So this is a function. Yeah. What's the fundamental theorem of calculus? So I will differentiate this function. So that would be like dy over dx. So that would be like the derivative of this function. If I integrated the derivative of a function, dx, what will I get? I will get my function back. So yeah, add this interval. Let's look at an example, and maybe that will like make it little bit more clear. So I have, this is my guy, like this is my function. Yeah, I want to find the first derivative of this function, like dy over dx. How to find this? I didn't show you how to. I showed you like with the limit, but how to find this? There is actually a rule. Like if I want to find the rate of a change of this function, the rule is, this is called the power rule. Like to find, like I have a function, to find the derivative of this function, the power rule is as follow. Like you see this guy, you bring it down, so like that would be like 3x minus 2, and you subtract 1 from here. So again, that is the called the power rule. So how does this work? Like you bring this guy down here, and then you subtract minus 1 from here. So let's do it again. So like the derivative, the rate of a change, so this is my function, the rate of a change of this function is, I bring this 3 down here, so that's like 3x, and then I subtract 1 from my power here, so that would be x by 2. Can I find like the second derivative? The second derivative, that would be like the rate of a change of the rate of a change, because like I have a rate of a change. Why not to find the rate of a change of the rate of a change? Why not? Yeah. So that would be, so the second derivative, the notation of the second derivative is written like this. So dy. So this is again, different notation. So that would be like the something like this, y bar, or yeah. And how can I find this? Again, power rule. So like you bring this guy down, you bring the 2 down. So this is 2 times 3, that is 6, and you subtract 1. Then you get like 2 minus 1, you get 1. Yeah. Can I find the rate of a change of the rate of a change of the rate of a change, like my third derivative? Yeah, why not? So my third derivative, dy, dy over dx. I mean, same thing. Yeah, like how you do it, like you bring, so this is to the power 1, so you bring 1 down, so 1 times 6, that is 6, then you subtract 1, from here, you get x to the power 0, x to the power 0 is 1, so basically you get 6. Yeah, so you see here, this is my function, this is the rate of a change of my function, this is the rate of a change of the rate of a change of my function, and this is the rate of a change of the rate of a change of my function. Yeah. So for example, if this function describe like some distance, that will tell you about like your velocity, and that will tell you about like your acceleration. Yeah. And that will tell you about like the rate of a change of your acceleration. Like so acceleration is the rate of a change of velocity, and that would be the rate of a change of acceleration. I think in physics this is called jerk. Yeah. But anyway, this is not important. Like these details are not important now. So now now what I did here, I was able to find like dy of dx. Now this is what this is telling me. Like it's telling me if I integrated like this guy, yeah, guess what I will get. So let me just like integrate this guy from a is equal to 0 to b is equal to x. I will integrate it through this interval. So if I integrated this guy, what this is telling me, like if I integrated this guy, I will get this guy. If I integrated this guy, I will get this guy. And if I integrated this guy, I will get this guy. Let's do it, yeah? You want to do it? So basically, what I will say here, and my integration from, this is like what I'm doing, a to b. So I'm integrating from a, which is equal to 0, to b, which is equal to z. And what do I want to integrate? I want to integrate like this guy. Yeah. And I'm integrating over dx. So if I integrated this guy, let's just do it here. So this guy is equal to what? This guy is equal to 6. Yeah, this guy is equal to 6. So I integrate 6 from 0 to x. We are doing in time here. I mean, not so bad. Okay, so I integrated here from 0 to x. And how do I do integration? Like just the opposite of what I did here. So that would be equal to, so like remember in differentiation, you subtract 1. Here you add 1 basically. So basically that would be 6. Like, so you can see this is x to the power of 0. Yeah. So basically that would be like you add 1, x to the power of 1, and then you divide by whatever you have here. So that's divided by 1. So it really doesn't make any difference. So that would be just 6x. Yeah. And I'm evaluating this from A to B. See, like this is exactly here. So I got, and I'm evaluating this from A to B. So from A to B, so that would be like 6. I substitute this 6x minus 6 to the power 0. And so that's 0. So I got like 6x. Yeah. Wow. What did I got here? I got this guy. That's the fundamental theorem of calculus. Yeah. Like you integrate the derivative, you got the original function. So that's like my original function. Now let's do it one more time. Yeah. So let's do it here. So here this is, I'm integrating from 0 to x, and I'm integrating this guy. So now this guy is like my second derivative. Yeah. I'm integrating my second derivative, like d to y over dx. And that is equal to, I just substitute this here from 0 to x. That would be like 6x. Sorry, here I forgot to add something. Just like dx. That's 6x dx. So if I integrated this guy, do you remember like what is the rule? Like, so you make something that looks like this. This is from 0 to x. And what is the rule? The rule is like you add 1 here. So this is x to the power 1 plus 1. So that would be 2. So x to the power 2. And then you divide by this new powers that you have. So you divide by 2. So if I did this, what do I get? Like 6 divided by 2, I got 3. Wow, does this look familiar? Then I substitute the x here, then I substitute the 0 here, then I got 3x to the power 2. So when I integrate this guy, I got like this guy. Wow, this is exactly what we want. Now, let me integrate the first derivative of the function, yeah? So now this is the last one. I'm just repeating it so that you get familiar with it. I hope this is not getting boring. But so you do like dy over dx, and what is, and I'm integrating this from 0 to x, and yeah, so basically this is what I want to integrate, 3x squared. And if I integrated this, guess what will I get? So let me undo this. Let me make all this clean, because now we are getting to the fundamental theorem of calculus. If I integrated this guy, like, what will I get? I will just get this guy, because that is the fundamental theorem of calculus. The fundamental theorem of calculus is telling you if you integrated your derivative, you'll get back your original function. So let me integrate this guy. So here, this will be to the power of 3, and then you divide it by 3. So 3 will go away with 3. Yeah. Then this is evaluated from 0 to x, and I get like x to the power 3. So I got back my original function. So what did I do here? Let me write it down. Like this guy, I found the derivative of this guy. If I integrated the derivative of this guy, I will get this guy back. So here is my original function. I differentiate it. I got like the derivative. If I integrate it, I'll get my function back. This is called like the fundamental theorem of calculus. But I know some of you are now thinking, I mean, why are we doing these? Like, why these things are important in life? And who cares? Like, I mean, who cares about fundamental theorem of calculus? And I have a function, I differentiate it and integrate it. Why these things are important in life? Well, I will show you now that this is central to like many of the equations that we deal with in engineering. They are based on the conservation law, conservation of mass, energy, and momentum. And I will show you like how this is central. Like all these, most of these equations that we deal with, they just can be derived from this guy. I will show you this in a minute. Okay, but before I do this, let me just like do it step by step. Yeah. So here, like consider a spatially differentiable scalar function u with one-dimensional system with bound AB. So that's similar to what we did before. So this is like my function. This is the derivative of my function. If I integrated this, I'll get back my function. Yeah, that's there's nothing new here. Now let's do this, take this like one step further. Like so more generally, a differentiable, like this is a scalar function. So it only has like a magnet like a vector function, yeah, in one-dimensional system with bound like a and b. So like consider here like this is like a vector function which has uh, like two variables like x and t. So this is like a function that's not only changing like an x but like a changing like an x and t. So this is like vector functions, and it would look something like this. Like, do you agree? So here like this you will so this is like a vector function, and it has like two variables. Like here, it would look something like this. So this would be like one-dimensional system, for example, that is changing with time. Let's do this at a more general form. So basically, here's the more general would be like a differentiable vector function, where R here, like see this guy, that depends on the spatial position vector. So that R is like another vector, like it's a function of x, y, z. Then like this guy, like this fundamental theorem of calculus, which we already understand, will be this guy here. Again, don't be scared from this. This is just like an introduction of what we will be doing over the next three module differential calculus. So differential calculus is like this guy here. Yeah, integral calculus is this guy here, and then differential equations, that would be like these guys here. So that's just an overview of what we will be doing. But what I want you to see here is I want you to see the similarity between this equation and this equation. So what does this equation mean? Basically, this equation is telling us something very important. It is telling us that you have this guy here, okay, and you have this guy here. Basically, like this partial omega A and partial omega B basically is telling you like so. This guy here means that over like this area, like what's happening over this area to this area. Yeah. And this guy here, your omega, that's basically your total volume. So if you are wondering what is this, and here, why is this partial? Because like you have one of them in the x direction, you have one in the y direction, and then you have like also in the z direction. But this guy is called like surface integral because this is what's happening across my surface. And this guy here, this is called like a volume integral because this is a volume, because this is what's happening inside like these volume, like representative volumes that I have here. So what is this telling you basically is that I have like a flux that is coming in, yeah, and a flux that is going out, yeah. The difference between what is coming in through my surface integral is equal to what is changing inside my volume integral. So I have a flux that's coming here, let's say, so here like from like let's say I have like 10 units that are occurring here, entering, like say 10 milligram or 10 whatever of a contaminant or anything, and 8 unit is leaving here. So what is accumulating inside? So I have like 10 is entering, 8 is leaving. This means that I have plus 2 is accumulating here. So this fluxes across the surface, like this 10 and this 8 are expressed by this guy. What is accumulating here, like whether it's a source or a sink. So let's say I have like 8 uh, 8 is entering here and 10 is leaving here. So I will have like 2 of these from like storage here will decrease by 2 because 8 is entering, 10 is leaving. This means I lost 2 points. So like gaining like this source or thing, like what is entering, like these flux that are entering and leaving are described by this guy. What is gaining or losing here is like described by this guy. So let me do another example. Like let's say 10 is entering and 10 is leaving. What does this like? So delta change in storage here would be like delta change in storage would be 0. And so like this guy, this is called like the diversion. So like this guy is called like diversion. Your diversion will be equal to 0 because, and that would describe the steady state. But what am I doing here? What I'm doing here, I'm just describing the laws of conservation. This is exactly the laws of conservation. The laws of conservation is what is coming in plus what is leaving your system is equal to the rate of a change. So the change of storage, like let's say like mass out minus mass in, that is equal to the change in storage. That's the conservation law. So basically, this guy describes the conservation law. Yes, this is a general formula from conservation law. From this guy, I could derive the conservation of energy. What is conservation of energy? That's Bernoulli equation. I could derive the conservation of mass. What's the conservation of mass? That's your flow equations. Uh, I could derive the conservation of momentum. So what's the conservation of momentum? This is like force equal to mass acceleration. All these like stress and structural analysis and everything. So basically, like this guy, you can derive from it many of these equations that we have been dealing with, like flow equation, forces, like anything that has to do. This is the general form of the laws of conservation. That's basically what this guy is. So I will, I think that's why this is important. Again, don't worry, like, so here, this is just like a summary. So this basically is telling you that this is your surface integral, this guy here, describing what's happening across the surface, and this is like your volume integral describing like the changes on your quantity inside like this volume, and this is called like this is diversion. And if you don't understand like these things, don't worry, that's exactly, this is just an introduction over these what we will be doing in these three module. By the end of this module, like when you will come back and look at this equation, just module one, differential calculus, you will say, okay, I know what does this mean. I know what is diversion. Yeah, I know that like divergence, this is like something, this is like a vector function here, and then I got like this scalar function here. And you will know this by the end of this module. Yeah, but if you don't understand this, don't worry. I mean, this is just an introduction. Don't panic, don't worry. This is just an introduction, and by the end of this concept will become like clearer and clearer. Yeah, but I just wanted to give this introduction so you see where this is going, and you will see like how from this guy we will derive, for example, like the flow equation, groundwater flow equation, or like general like flow equations. Yeah, just from guy that looks like this. Okay, so see you in